Hi. So we're gonna jump right in after the conclusion of the last video about confidence intervals, and we're gonna talk about hypothesis testing. And so the basic idea behind hypothesis testing is a researcher or a scientist makes a claim about something that they believe is true, and then we gather data, and then we see whether or not this claim is supported by the data or not. And so let's once again use our sort of made up example from the last video and talk about purple microelephants. So, a researcher believes that purple microelephants mm, fence on average weigh more than 120 pounds. So she weighs 40 of them, and so she weighs 40 of them, and they have average weight 125 pounds with the standard deviation 100, let's say 20 pounds. Is she right? All right, so she thinks that on average they weigh more than 120 pounds. She grabs up 40 of them, weighs them, and their average weight of the 40 she weighs 125 pounds. Standard deviation of their weight is 20 pounds. So, is she right? And if you're paying attention uh, to the confidence interval video, then there is a fairly straightforward answer to this question in some sense, and that is, how are we supposed to know that, right? We don't know whether or not uh, her hypothesis here is true or not. So in this particular instance, uh, these particular elephants that she weighed did in fact on average weigh more than 120 pounds. But we don't know whether or not, we just got lucky or unlucky by picking 40 particularly heavy elephants. And hey, even if their average weight was less than 120 pounds, it's still possible that we picked especially light elephants and that in fact the average weight is more than 120 pounds. So we don't know for sure. But just like in the confidence interval situation, if we don't uh, force ourselves to conclude things with 100% confidence, if we're willing to accept 99% confidence, 95% confidence, 90% confidence, we can get a range of answers that satisfy, right? Or a range of potential solutions to say what the meaning of that microelephants are. And so in our case, it's much the same. If we don't need to be 100% accurate, if we can accept a 1% chance of being wrong, a 5% chance of being wrong, uh, probably not more than 5%, but I guess you could, then we could take a shot at trying to answer this as well. So, what we what we're going to do now then is talk about, how exactly one would do that, and the philosophy behind uh, how we should think about this that will drive the methodology we will use. So, um, researcher here is making a claim, and so let's talk about what this claim is. And this claim is called the alternative hypothesis. And it's denoted HA. This is the thing that our researcher is trying to establish. And in our particular case, our alternative hypothesis is that the average population mean of purple microelephant weight is in fact greater than 120. Right? And what we have then is a sort of default. What if we can't show this claim? What if we don't have enough information to show it, or if the data suggests otherwise? Then we have something called the null hypothesis. And that's denoted H naught. And in our case, and this is a little confusing at first, we would say that the mean the mean weight of the population mean weight of purple microelephants could be 120. Now, many of you are maybe asking yourselves why it couldn't be less than or equal to 120, and in some sense that might be the right way to think about this, but there's a sort of technical reason why the null hypothesis is in fact that the mean is 120. But the way you want to think about it is that, if we can't show that purple microelephants are more than 120 pounds, then it's possible that they are 120 pounds on average. And that's the way to think about this. And so what then is the relationship between the alternative and null hypothesis? We want to, maybe I should go back here, we want to think about the alternative hypothesis as a guilty verdict in a jury trial. And we want to think of the null hypothesis as the not guilty verdict. And so in science, we don't want to accept a new claim unless you show very, very strong evidence that that claim is true. Otherwise, we default to that maybe that claim isn't true. So in this case, our researcher puts forward the claim that the average weight of purple microelephants is more than 120. If she can't show that this is true, then she has to default to, well, maybe they could be 120 pounds, right? Just like in a criminal trial, we default to a defendant being not guilty unless you can show strong evidence to prove that they are in fact guilty. And so what we have then is a sort of similar setup to a sort of similar setup to a jury trial where, well, two things for sure could be true. Either, let me pick a color here. Let's say, so HA could be true, HA could also be not true. And so we would maybe think of this as defendant guilty, and the HA be false would be defendant innocent, right? And so remember that in a jury trial, you default with an assumption of innocence, right? You default to not guilty. And we have to demonstrate with sufficient evidence that someone is guilty. So, in a similar spirit, when we're doing a hypothesis testing claim, we default to the null hypothesis. We default to, well, maybe our statement isn't true, and purple microelephants could weigh 120 pounds on average, and you have to show otherwise. So, the two things that can happen here are either that we accept H naught, or we reject H dot. And so, and then the corresponding sort of criminal justice analogs will be accepting H naught would be like a not guilty verdict, and rejecting H naught would be like a guilty verdict. So, if the defendant is in fact guilty, right, and you find them guilty, so if the alternative hypothesis is true and we reject it all, then that's good, right? That's exactly what we would want to do. And so we'll put a big old smiley face right there because that's a good thing. All right. If your defendant's innocent and you find them not guilty, that's also a good outcome, right? We don't want to assume guilt unless we have the evidence to show that they're in fact guilty. So, and similarly, if the researcher's claim is not true, then we probably shouldn't accept it, right? And so if that happens, that's also good, right? But then either of these two boxes are not so good, right? In one case, the defendant is innocent and we find them guilty, that's bad. In another case, the defendant is guilty and we don't find them guilty, and that's also not good, right? And so we have names for these two types of error. So this over here is a type 2 error, and this in the bottom left corner, you may guess, is a type 1 error. And just like in a criminal trial, this one is much worse. All right, and let's think about why that is. Let's go back to scientific reasons. Let's say, that purple microelephants in fact do weigh more than 120 pounds on average. And you will get a bunch of evidence, you weigh them, and it doesn't really seem conclusive. It doesn't seem like the average weight is that different from 120. Well, yeah, okay, then we don't, jump out the window and say for sure they weigh more than 120 pounds. You can always go back and conduct another study. You can always go back and gather more data. You can always, go back to the drawing board, regroup, and then try to show this again. But if purple microelephants weigh 120 pounds or less, and you jump out the window and say, no, I know for sure they weigh more than 120 pounds, then maybe other scientific research gets built on top of that with that assumption. But all right, they weigh more than 120 pounds, therefore this, therefore that. And all sorts of conclusions get drawn, and none of them are true. We don't want to add things to uh, either the scientific literature or any other bodies of academic knowledge or knowledge at all, unless we're really sure that they're true. So we don't want to start claiming things are true when they're not, right? It's better if we're not sure just to accept the null and then hit the drawing board and maybe try to show them again, right? And so this is going to be the philosophy that we have going forward. And so, uh, going back to our analogy here, let me pick a different color. The null hypothesis or the default statement is the thing that we will assume. And so the whole idea is that we assume that the null hypothesis isn't true, and our goal then is to show that that really can't be the case. So again, a criminal trial is a good analogy for how this works. So let's say that uh, you have someone who is accused of some crime. We would assume initially that they're not guilty, right? Everyone's granted the presumption of innocence. Now, uh, it's up to the prosecutor then to demonstrate sufficient evidence to show that there's no way that this person could be not guilty. That if this person was not guilty, all these things that they observe wouldn't have happened, right? That there is no acceptable explanation for that. And if they can show enough evidence like this, then so through evidence, we can go from the assumption here to the uh, the alternative claim if the evidence is sufficiently strong. If the evidence is not sufficiently strong, then we have to stay here. So one, or maybe this is the right place to. No, let's use this one here. So accepting the null hypothesis, it's really important to note that accepting the null hypothesis is not the same as H naught is true. Right? This is a really important distinction to make because if all it means, if we accept the null hypothesis, is that the evidence presented wasn't strong enough to go from our null hypothesis to an alternative. And that could be because that H naught is true, right? So in this case, it could be because the average weight of purple market elephants is 120 pounds. But it could also be because your sample was too small, that you just got unlucky in terms of the sample that you measured. It doesn't necessarily mean that the alternative hypothesis is wrong if you assume H naught. It just means that your evidence is not strong enough to make that change. And so that's a really important thing to keep in mind as we move forward here. So this is the basic steps for hypothesis testing. the first thing we'll do then is assume H naught. Right? We're going to assume that the null hypothesis is true. And then our next step is to compute the probability that results like the one seen occur. And this probability is something that's called the p-value. All right, so what we'll do is we'll assume that the null hypothesis is true, and then all right, if the null hypothesis is true, then how likely is it that the things that occurred in an actual experiment or observation will occur? So in our case, that's like saying, okay, let's just assume for the sake of argument that purple microelephants do weigh 120 pounds on average. Then what's the chance I weigh 40 of them and get that they have an average weight of 125? So maybe that's pretty likely, right? Maybe for given the variation, the standard deviation of microelephant weights, they're variable enough, or something like that's not so uncommon. But maybe that's really, really rare, and it would be ridiculous to think that that something like that could occur. So the next step then is to compare the p-value to the accepted level of significance which we're going to call alpha. And by default, alpha is 5%. And so what alpha represents in this case is essentially a uh, level of error that we're willing to incur. So let's just, for example, use 5% as our alpha. What we're saying is, all right, we assume the null, and what's the chance that results like the ones that occur happen? And if the chance of something like that occurring is less than 5%, then we'll say, okay, that's really not very likely. If it's less than 5%, it's a lot more likely maybe that the null hypothesis is wrong. However, if our p-value is bigger than our alpha, we say, okay, there's more than a 5% chance that if the null hypothesis is true, that something like this could happen. Maybe the null hypothesis is true. And so the final step then is either the p-value is less than alpha, or it's greater than or equal to alpha, And if it's less than alpha, we get to reject the null hypothesis, the null hypothesis. Otherwise, we accept it. All right. So hopefully, all of that is sensible. And so let's go ahead and apply this to our situation here. So if we apply all of this thinking to our purple microelephants, remember that we've measured enough of these elephants, 40 of them, for the central limit theorem to assure us or give us, suggest to us that our distribution of the average weight of 40 microelephants is approximately normal. And we're assuming the null, right? So we're assuming that the mean is 120 pounds. And so I'm going to write that down there because we assume H0, right? And then we should also remind ourselves, of course, that the mean of this distribution is 120 because of the null hypothesis. And the standard deviation of this distribution is the standard error, which in this case is 20 over square root 40. Right? If we go all the way back to the beginning, we note that that's our n and that's our s, right? And this 125 is our x bar or point estimate, right? So going forward back here, so here we have 120 pounds as our mean, and somewhere out here is 125 pounds. And that area here, this thing is the p-value, right? It is the probability that we see a result like 125 pounds or more, since the claim in this case is that the average weight is more than 120 pounds, right? So, what is that p-value? Well, we can go ahead and break open our normal curve calculator. So we know the mean of our distribution is 20 pounds. 20 over the square root of 40 is the standard deviation. And we want to know, let's say between 125 pounds and let's say 1,000,000 pounds. Give it a second. And that's not so great, right? Our p-value here is about 0.569, right? Which is definitely greater than 0.05. So we weighed these 40 elephants. We weighed these 40 elephants. They had average weight of 125 pounds, and that's not quite strong enough evidence to say that for sure purple microelephants have to weigh more than 120 pounds. That there's some chance that maybe if they weighed 120 pounds, that there's about a 5.7% chance that we'd see results like this. So that's not that uncommon. Maybe it's just due to chance. So in this case, we would have to accept the null hypothesis. All right. So let's do something slightly different. Let's change up the null hypothesis. Let's say there's a different researcher in this research group, and her hypothesis is just that the average weight of purple microelephants isn't 110 pounds. All right, so if the null hypothesis that the average weight isn't 110 pounds, then the null hypothesis, well, clearly that means that it is 110 pounds. So we go ahead and assume the null once again, and let's suppose we have the exact same data. Say, all right, if this researcher, if she decides that that the alternative is that purple microelephants don't weigh 110 pounds on average, then let's assume then that they do weigh 110 pounds, and let's see what the probability is of getting results like the ones we've seen. So the difference between what we just did and what's going to happen here is what it means to be results like what we saw. In this case, like what we saw would mean 125 or more, or this is length 15, so go over here, 95. Or less. And because our alternative hypothesis is that you're not 110, either really large or really small results will demonstrate that the average weight is not 110, right? If you weighed 40 microelephants and they weighed 8 pounds on average, we'd say that. They probably don't weigh 110 pounds. If they weighed 1,000,000 pounds on average, we'd probably say the same thing. As our p-value then is the sum of these two things, right? Which I could, calculate this tau, calculate this tau, calculate this tau, add them to each other. I could calculate this tau and double it because these two taus are identical, or I could find this middle area here. And for now, that might be easier. So in this case, let's say our mean is 110. We got all the exact same data. So what if, so the two things I could do is I could go between 95 and 125. And this area here, is 0.9999. How many nines? 5 nines, 979. Right? And so that means the errors of my tau has to be less than 0.12345. Then the p-value then is 0.1234521. I won't even 0.1234521. There we go. So definitely less than 0.05. And we should note that I could have taken gone up to 1,000,000. That's too big. And I get 1.50718 times 10 to the minus 6. What is it? 0.50718 times 10 to the minus 6. And I want to double that, right? Because if we look at a picture here, that's just one of these tails, right? And there's two of them, so if I add these two tails together, that's twice the area. So I go ahead and double that area, and I get 0.00021 as well. So same thing, right? And so in this case, if purple microelephants only weighed 110 pounds on average, then the chances of seeing something like what we're looking at right now is less than a percent of a percent. It's about 2% of a percent. So that's so unlikely. It's so ridiculously not possible, or not impossible, but it's so ridiculously not likely that it's far more plausible that maybe on average they do weigh more than 110 pounds. So in this case, we would reject. H naught. All right. We're definitely less than the 5%, so we're good. And that basically demonstrates in practice or the theory and reasoning behind the methodology for hypothesis testing. In the other video, we already introduced this calculator, which is the Z hypothesis testing calculator, and we use this to find confidence intervals. Now we should note that we can also use this to do hypothesis testing. So let's say I have a mean of 40, 40 data points, mean of 125. That's what we measured. Standard deviation 20. This is all information about the data, right, that we were given. So in the first hypothesis, we said, all right, my claim is that the average weight of microelephants is greater than 120 pounds. We assume an alpha of 5%. And our alternative hypothesis, right, when we look at the alternative hypothesis, is that the true mean, or mu, is greater than H naught. So we click on that, we get this Z value here, the Z.1458, that's the Z value of the 125 with 120 at our mean. This green region here is how much the elephants would have had to weigh on average for us to accept or reject the null. We're not in the green region, so we can't reject the null. And our p-value here tells us we can't reject the null, right? It's too big for the 5%. On the other hand, in the second problem we did, we went from 120 pounds to just not being 110. We said that our true mean is just that we're not 110. And so if a purple microelephant, if 40 purple microelephants on average weighed more than 116.2 or less than 103.8 pounds, we would call that strong enough evidence to reject the null. And that's equivalent to the average weight landing in either of these green regions. And lo and behold, our 125 pounds that we measured is definitely in this green region right here, right? and the p-value here is absurdly small. It's 5 zeros and a 2. So we can definitely say that the average weight of purple back elephants with confidence is not 110 pounds. All right, there are 2 other chapters basically on hypothesis testing and confidence intervals. The philosophies behind those chapters are completely identical to what we just covered. So, if you can accept everything we've done up until this point, then everything going forward is just variations on this theme. That's pretty much all that's going to happen for at least the next 2 chapters. So, hopefully that was helpful. And this is pretty much the end of chapter 4. And the next time I record a video, it'll be about homework problems that you guys asked for or about chapter 5.